Okay, well, first, thank you for the invitation to present my work. So today I will tell you about this matrix duality in twistor space. It's some work in progress with Simon Caron-Hood and Beatrix Millman. So the context is n=4 super-Young Mills, and the main observable I will be telling you about is this correlator of determinant operators. Determinant operators, they are important because they are dual to giant gravitons in the ADS bulk dual. There is also a fact that is maybe not well known, but it is easy to see that these determinant operators can be understood as generating functions of all single trace BPS operators of the theory. So basically, if you have this determinant and you use this simple identity that the log of determinant is the trace of log, then you can see that you can expand and obtain first the smallest BPS operator, the 20 prime operator, but also all the higher BPS operators, which are dual to Kaluza-Klein modes of the graviton in ADS. Another fact why these determinants are important is because a couple of years ago with Simon, we established or we conjecture a new duality of the correlator of these determinant operators with massive amplitudes in the Coulomb branch. So studying these correlators give us a way to get access to these massive amplitudes in the Coulomb branch. Of course, it would be nice also to develop some integrability tools to do these computations at finite coupling. That would be something for the future. But in this talk, I will just concentrate on simpler objects, which are just the loop integrands. The loop integrands are the objects that when you integrate, you will obtain the full loop corrections to the correlator. And they can be computed by a method known as the Lagrangian insertion method, which basically tells you that if you want to compute the L loop correction to the correlator, you need to compute this correlator of the determinants with L Lagrangian insertions. The advantage of studying these objects is that they are simpler. They are just rational functions. And it's possible already at this level to observe some hidden symmetries that in many cases are inherited by the integrated form of these correlators. In particular, today I will be highlighting that these integrands have a hidden symmetry, which is a 10D structure, which combines space-time and R-charge space. And in fact, it is this 10D structure which is at the core of this conjecture, this new duality between correlators of determinants and massive amplitudes. So first, I will start by going through just the free theory case where there are I'm not gonna do any Lagrangian insertion, just study these determinants on the free theory and show you that already there you can see the 10D structure just by doing big contractions. So when you compute these correlators of determinants in the free theory, you can expand this determinant in terms of an infinite sum of single traces, as I showed you, and then just do the big contractions. Because there are an infinite number of vertices, the way you will do big contractions between each pair of operators is actually an infinite sum. You will get an infinite sum of the case where you have just one single connection or two propagators or three and an infinite. And in fact, this infinite series forms a geometric series, and it can be resummed. This resummation is what gives you this 10D structure. After resumming all of these propagators, we get an effective propagator, which instead of having the 4-dimensional pole, it now has a 10-dimensional pole that composes the space-time with R-charge. One question you can ask is whether you can find a reformulation at the level of the Lagrangian, which uses this effective propagator as the propagator. As I was telling you on the original formulation, the way this arises is only after performing a resummation, once you're doing the computation. But there is an alternative way, which by using something called matrix duality, you can reformulate n equal 4 and see that the effective propagator now appears as a propagator in this new formulation. This matrix duality is a generic relation in matrix models. It identifies the correlator of K determinants in a Gaussian matrix model of matrices of rank n, with a correlator of n determinants in a matrix model with rank K. So basically, here on the left-hand side, you have these K determinants in this matrix model of rank n. And then on the right-hand side, you have a similar object, but now what was the number of determinants and the rank of the matrix, they get exchanged. Now you get matrices of order K by K and n determinants. This is just the relation in a matrix model, but we can, of course, apply this on our free theory of n equal 4 super Mills. What we need to do now is to decorate this with some space-time dependence. This formula would be only for matrix for zero-dimensional matrix model. But here, this is the upgrade, which actually is due to Komatsu. Sorry, because I forgot to, I didn't have time to add many references. Here, this is the version of the matrix duality, but now apply including a spacetime. So the Gaussian includes the usual kinetic term of the scalar field. Here we have our determinants, and this is equal to now a correlator of the determinants of NC determinants, where NC is the rank of the gauge group. And now we have this other kinetic term, still with this propagator Dij, which is, well, forgot, this Dij is y over x, Yij, xij. But it is possible to see that after expanding the determinant, there will be now a different effective propagator. For this, maybe I should clarify that what I'm calling matrix duality, and I'm presenting mathematically at the level of the identity, the equality of two correlators, is actually just the well-known graph duality. So in order to see that, you can expand this determinant in terms of single traces using the well-known identity log det equal trace of log, and you will get an infinite number of vertices. And these vertices, they will be dual to faces on the original model. So here on the left panel, I have here in black the B contractions, the original B contractions that you would do for the free theory of n equal 4. Here I'm kind of using some planar notation. And after doing B contractions, you get a graph that has different phases. And now in blue, I'm drawing what's the dual, what's the representation, the Feynman diagrammatic representation in the matrix dual. And what you will observe is that now what were phases are traded by vertices. And these vertices correspond to these traces of rho that come from the expansion of the determinant. And one fact we can observe is that the determinant itself comes with a quadratic term, which can be used to correct the original kinetic term. And once you absorb this quadratic term on the full kinetic term, you get a new kinetic term that contains this effective propagator, the 10D propagator. And now the vertices just start from the cubic up to, well, infinite balance. So this is one formulation that allows you to see that there is a hidden 10D structure when you consider the correlator of these determinant operators. Now, we would like to see this structure, but for all the loop integrands. So now we need to find a way to perform this matrix duality when we turn on more fields. So here, because I was just doing free theory, I was able to restrict n equal 4 just to the kinetic part of the scalar. But now that I'm gonna include these Lagrangian insertions to compute loop integrands, I will need to use the full n equal 4 with fermions and gluons. What I want to show in this talk is the tools that we develop in order to be able to perform this matrix duality for these loop integrands. And the result will be similar, that now we will get a model that will have a manifest 10D structure. And that we will use to justify that there is a 10D null limit that we can use to make a connection with massive amplitudes in the Coulomb branch. Okay, so let me go on, and of course you can ask me any question. Feel free to ask me any questions if something is not clear. But so for now I will go on and address the case of the loop integrand. So I will have this correlator of the determinants, but now I include these Lagrangian insertions. Here I'm presenting what exactly it means to have these Lagrangian insertions. These integrands, they are Born-level correlators in self-dual Young mills. So n equal 4 super Young mills, the action or Lagrangian of n equal 4 super Young mills can be written as a sum of two terms. One that is just the self-dual part, and another non-self-dual part, which is what we call the Lagrangian, the chiral Lagrangian. So here I have the explicit form in terms of the fields of n equal 4. And what we want to compute is correlators of these determinants that I presented before with these Lagrangian insertions, using as action the action of the self-dual part of n equal 4. And we want to do the matrix duality of this partition function and to obtain a 10D structure. However, there are some obstacles, because the matrix duality I presented is better applied when you are dealing with some Gaussian action. So determinants computed with a Gaussian action. However, this self-dual part of n equal 4 is, when you inspect it, you notice that it's not really a Gaussian. It contains some cubic terms, and that's already an obstacle. However, there is a solution which requires uplifting n equal 4 to twistor space. The advantage of going to twistor space is that it's a higher dimensional space and it has more gauge freedom. And we can use as an advantage the extra gauge freedom to choose, to make a gauge choice that is not available from spacetime formulation, but only on the twistor formulation. And there is a gauge choice that allows us to make the twistor action Gaussian. And once it's a Gaussian action, we can apply the matrix duality. So that's the first obstacle that can be addressed uplifting to twistor space. And the second obstacle is that this chiral Lagrangian I'm showing is not really a determinant. And as I was showing you before, what I call matrix duality is an equality of correlators of determinants. So I better express this as some correlator of determinants, including the Lagrangian insertion. The Lagrangian insertion is not a determinant in the original spacetime formulation, but it turns out that when you go to the twistor formulation, it is a determinant. So here these are the two reasons why I am invited to go to twistor space in order to perform the matrix duality. So this is what we are going to do next. We are gonna go to twistor space. Okay, but first, yeah.
It's a bit basic, but what is a twistor?
Yeah, so it will come next.
Okay.
I will explain that next. Okay, so well, before to uplift into twistor space, I'm going to well, just make a brief review of what is this half-BPS condition. These determinants I'm considering, which are dual to giant gravitons and are generating function of all 1/2-BPS operators. They are also, of course, 1/2-BPS. And so I need to explain a bit of how this half-BPS condition works. So for that, we are going to use superspace. And in the formulation of n equal 4 in superspace, we have 8 chiral and 8 antichiral variables. The condition, so normally a supermultiplet on this superspace will depend on these 16 variables. But the condition that is 1/2-BPS is the condition that it only depends on half of these variables, on half of the chiral part and half of the antichiral part. So 4 chiral and 4 antichiral. In this talk, I just specialized to the case where I set the antichiral part to 0. So all I will be caring about is going down from the original 8 chiral to just 4 chiral for the BPS operator. In order to make the way we parameterize the choice of which half we are taking, that corresponds to the use of this R-charge polarization vector. The polarization vector that tells you the content of scalars of my operator is also the vector that we use to select which half of the A chiral we are using for our operator. So this polarization vector is a null vector that satisfies this condition. And because it is null, it has this twistor-like decomposition in these more elementary vectors. And we can use these more elementary vectors to decompose the original 8-dimensional superspace, the chiral part, into 2 halves. So here we use this vector to select 1/2 that we call theta minus, and the other half is theta plus. Under this notation, the BPS condition is the condition that the BPS operator only depends on the half theta plus. So here I'm just stating that taking derivatives with respect to theta minus is 0. So this can be also written in terms of using the R-charge polarization vector. Just to give you an example of how a 1/2-BPS operator looks like in superspace, here I'm representing the stress tensor multiplet, but only the chiral half. Remember, I'm setting theta bar to 0. So if you are interested just on the chiral half, this supermultiplet first starts with the scalar operator, which is what we call the 20 prime operator. It's just an operator containing the scalars and with the polarization vector y telling you which content of scalars you choose. And then the supermultiplet climbs, and you get you get up to 4 degrees on Grassmann variable. For each of these groups, there are multiple representatives, but on the final one that is order 4, you get again just 1. Just like on the bottom there was one element, on the top there is again just 1 element, and this 1 element is what I call the Lagrangian interaction term. So the 20 prime operator and the Lagrangian interaction term, they are actually on the same supermultiplet. And what I'm going to do is to also consider a supersymmetric version of the original determinants I introduced, because this supersymmetric version will also contain the Lagrangian insertion. So the way it works here is you should think that if you look at the bottom component, this determinant corresponds to adding to this 20 prime operator all the tower of Kaluza-Klein modes. If you do that, then you will obtain this bosonic determinant operator. And if you do the same for all the other elements of the supermultiplet, you add all of all of its Kaluza-Klein mode, we're going to obtain all the SUSY superpartners of this determinant, and all of them can be repackaged together on what I call the SUSY version of my determinant operator. So what I'm going to be really addressing is this correlator of SUSY determinants, because from here I can extract as a component the correlator of determinants with the Lagrangian insertions. They are all, this object is really the generating function of all of them, the bosonic determinants and also the Lagrangian insertions. So this is the object that I'm going to be on which I'm going to be using a matrix duality. Okay, so now we turn to twistor space. So right here, well, I don't have a good slide for explaining a bit of twistor space, but let me see. So in original space-time, we have this, let's say, this point X. Here on twistor space, so here I'm on R4, and twistor space is, the space is CP3/4. The /4 is for the supersymmetry, CP3 is the projective space, and the uplift from space-time to twistor space corresponds to uplifting this point to a line. So a point on space-time corresponds to a line on twistor space. So this is the main relation. And well, furthermore, there is another nice relation that if you have another point here, x1 and x2, and these points are null separated. So as I said, the point x1 will be one line on this twistor space. The point x2 will be another line. So you can just draw it like this. But if they are null separated on the original space-time, then these two lines in twistor space intersect, and this point of intersection can be related to the null line in space-time. So the way you can do the map or understand the map is that, as I said, a point maps to a line, but then null lines in space-time map to points in twistor space. So this is a brief introduction to what I call twistor space. And this twistor space, as I said, is higher dimensional, since a point now becomes a line. And the nice advantages that it has is that it has more gauge freedom, and we are going to use this extra gauge freedom as an advantage to make our action Gaussian and then be able to use the matrix duality. So here, I have the formulation of n=4 in twistor space. It has two parts. This first part is some holomorphic Chern-Simons term, and the second part is some determinant operator. And these two parts actually match with what I presented previously on n=4 as a formulation on the self-dual part plus some non-self-dual part that I call the Lagrangian interaction. So here, the twistor space has a natural way to represent n=4 also as an expansion of n=4 around the self-dual part. Here, I think I forgot the coupling, but there's a coupling here. Right. So, well, here I also have another gauge field. This is not the gauge field on the original space-time. It is, of course, related by the Penrose transform, and it also has an expansion in superspace in twistor space. And here I have a typo. This should be eta, but this is the Grassmann variable. This is the Grassmann variable of twistor space, and is related to the original superspace by this incidence relation, contracting theta with this variable lambda where lambda is the coordinate that lives on the lambda is the coordinate that parameterizes the line on this twistor space. So the lambda lives on a CP1. Right. So as I was describing, this part here is the representation of the Lagrangian interaction in twistor space, and it looks more complicated. It is a determinant, but it is possible to see the equivalence if you make a gauge choice that we can call it like the space-time gauge choice, which makes this action here go down to the action I presented before. So there is a gauge choice that this determinant part, which if you expand in single traces gives an infinite number of terms, there is a gauge choice that makes that infinite series truncate, and it will give you just the 3 terms that I show you here on the space-time formulation. So there is a way to go down from here to the original space-time formulation, but we are going to use a different gauge choice. We are going to use a gauge choice that makes this a cube term vanish. So this a cube term here in twistor space is the analog of this 3-valent vertex of fermions and scalars, the one that was making the action no Gaussian. But here, now that I have the freedom to make a different gauge choice, I will make a choice that makes this a cube vanish, and then I will just be left with some really Gaussian term. So this is addressing the first point, that I get an action that is Gaussian. And the second point, let me explain more, is that the Lagrangian interaction term is now a determinant operator. And in fact, it's a determinant operator from which you have to extract the component with the maximal number of Grassmann variables. As I said, there are 8 thetas, so here you integrate over the 8 of them and you extract the top component. But so I should say this formulation is due to Witten. But later, Sokachev and Mason and collaborators, they realized that if you integrate less, it means like if you don't reintegrate over the 8 theta variables, but you just integrate over half of them, let's say the theta minus, you are going to get not only the Lagrangian interaction term, but actually you're going to get the full formulation of the stress tensor multiplet in twistor space. So I just remind you that this stress tensor multiplet is the one presented presented here in the space-time formulation. And now in twistor space, it can be obtained from this same determinant, but now just integrated half of the variables. And of course, then it has an expansion in the theta plus half that includes the 20' bosonic operator, the Lagrangian interaction as the top component. Here, it looks a bit different, but it's actually just a representation of how you can represent the determinant by including some extra auxiliary fields, in this case alpha and beta, to have a partition function that when iterating out alpha and beta, you get back to the determinant. Now, what I would like to do is to get inspired by this formulation of the stress tensor multiplet, which is just the multiplet of the 20'. But now I want to make an extension of this formulation to get the full determinant. The determinant, which is the operator that contains this guy, but also all of its Kaluza-Klein modes, all the tower of Kaluza-Klein modes. So we are going to do some slight modifications of this formulation here. Basically, what we realize is that instead of integrating out the variables at the end, we should actually move this integration at the interior, at the level of this action. So what we do is we supersymmetrize this CP1 line. The CP1 line is the line, but as I explained, points on space-time, they become CP1 lines on twistor space. This determinant has support only on this CP1 line. And originally it has no supersymmetry, but now I'm going to include some supersymmetry, and I claim that that gives me the formulation of the determinant instead of just the stress tensor multiplet. So adding SUSY, make supersymmetrizing the CP1 line means including these variables psi, which is just the contraction of the theta minus with the coordinate of the CP1 line. And this action here is similar to the previous one that gives the stress tensor, but now I make these auxiliary fields alpha and beta also depending on these extra Grassmann variables. And I also need to include some extra mass term for the auxiliary variables. And this is one of our main claims. This gives you a formulation of the full determinant, which is the 20 prime plus all Kaluza-Klein modes, which we obtain just by supersymmetrizing the original CP1 line of Witten and including some two supersymmetries there. The effect is similar to the previous case where you are removing the dependence of theta minus. As I explained, a BPS only depends on theta plus, but we do it more on the inner side. And the result is, again, an operator which only depends on theta plus and is BPS operator. And it gives you, as the bottom component, the original bosonic determinant plus all the SUSY partners. Right. Is there any question so far?
So this is the you said that this is a proposal, or that you actually you are able to test it, right? Or...
Yeah, so we tested when we do the computation of correlation functions. That's the way to test this formulation. What this formulation guarantees is that we are obtaining an object which is BPS, which is 1/2 BPS. And right, but then we have not really checked component by component that we obtain the SUSY partners that I claim here.
But in principle, you could.
Yeah, that's the claim, and it could be right. So this is here we are talking just about one single operator, and you can make this more explicit, because here I am using these auxiliary fields alpha and beta, but you can integrate them out. To integrate them out, you use their propagator, which I'm presenting here, is some Grassmannian delta function with a sheaf of 1 due to the mass term. And if you integrate out this alpha and beta using their propagator, you're going to see that this SUSY determinant is an expansion in terms of it's an infinite sum in terms of these vertices, where these vertices, which are traces of the gauge field, they are addressed by these propagators of alpha and beta. If you further integrate out all the CP1/2 variables, what you should obtain should be something that you can actually check component by component, whether it gives you this bottom component and all the SUSY partners. So this is one thing that you could do to make to decompose explicitly this proposal into components and check that you obtain the actual SUSY partners. We haven't done that. We actually decided to directly compute the correlators of this operator, and then you can check that the result corresponds to the non-resolved, to the few non-results for the correlators of determinants. So let's that would be one check. So and yeah, I should also say that so there is this original formulation of the Lagrangian insertion term, of the Lagrangian interaction or stress tensor multiplet by Witten or Sokachev-Mason. And then later, Staudacher collaborators, they made a proposal for what would be the twistor formulation of Higher-Kaluza-Klein modes, Higher-BPS operators.
Yeah, right.
Right. So our proposal is a compact proposal that repackages all of that. So another thing you can do is to check that this proposal indeed is equivalent to Staudacker's proposal. And in order to do that, you need to integrate out this alpha and beta. But it's not as straightforward, and so it requires some computation. But there are these sanity checks. You can make a check against a previous proposal that gave you the formulation of individual Kaluza-Klein terms. Now we have a compact one that repackages everything, and you can check that indeed it reproduces one by one the proposal by Staudacker. But here we are going to follow a different path. So what I describe is that if you want to make a check of how the operator looks like, you need to integrate out alpha and beta. But we follow a different path. We integrate out A, and we are going to get a theory of alpha and beta. So doing this step of integrating out the original gauge field, this is the first step that we need in order to do the matrix duality. So here I have this graph that is just representing how you integrate out alpha and beta by the propagator, and then you just get a vertex on A.
Yeah.
But now I'm going to integrate out A, and I'm going to get a vertex on alpha and beta. So this is the next part of the talk, where once we already have a proposal in twistor space, a novel proposal for the determinant operator. Now we're going to use it to compute correlation functions, but we're going to do it by using this matrix duality. So our goal is to compute this correlator of the SUSY determinants, which is a partition function in self-dual Young-Mills, but now rewrite it in a formulation in some dual matrix model with a more explicit ND structure. So graphically, the matrix duality is a bunch of steps where you integrate out some of the original fields, and then you need to integrate in some extra fields to get the final formulation. So this is the type of diagram that you will obtain on the original theory that contains the gauge field and alpha and beta. Integrating out the gauge field A graphically corresponds to going to these graphs and collapsing this propagator. Collapsing it such that every time you see this part of the graph, you replace it by some 4-valent vertex. A 4-valent vertex that depends on alpha and beta, and which is actually in space-time is bilocal, because this I and J, they label the determinant. So originally the determinant lives here. This is the determinant operator. They send between them, they send propagators of A. But now we integrate out this, we collapse into this 4-valent vertex. And now this 4-valent vertex, it knows about these two space-time points of these two determinants. So, but that's okay. Graphically, it's still some 4-valent vertex. Just it knows about two space-time points at once. And then the final step, well, the next step for the matrix duality is to open up again this 4-valent vertex, but now let's say in a different direction. So here represented by this vertical direction, I get the same graph, but now torn by some angle. But now the difference is that we get 3-valent vertices that are also bilocal. They know about two operators at the same time. And at the end, to get the final model, you now integrate out alpha and beta. You can integrate out, you can integrate out alpha and beta and get just a model of this new raw matrices. these are the steps that you need in order to graphically trade the faces by vertices. If you follow these 3 steps, and you start with a graph with certain faces, you can see that you follow these steps, you will see that these faces will turn into vertices, and you will get the graph dual or matrix dual. Here I'm just presenting the result. It is similar to the free theory case where I only had the scalar, but now I have an extra addressing, which is this CP1/2 propagator, the propagator of the alpha and beta auxiliary fields. So this is CP1/2. But it's a CP1/2 propagator kind of on shell, because so this is the CP1/2 propagator lives here. It is this, it lives on this line. And when we integrate out the propagator A, this propagator is actually some kind of delta function. So it will modify this CP1/2 propagator to some on-shell version. And that's why I just put some tilde there to specify that now this CP1/2 propagator now lives on the variables that, it depends on the spacetime variables of the determinants, of the determinants in the correlator. Again,
but when you say that you are integrating out and integrating in, like integrating out here actually means like going for some specific diagrams and computing loop by loop and see how you change from how you repackage everything in terms of a new vertex, or is something more like a level of some graph thing and you just propose some behavior? It's like a perturbative computation that you can do as you usually do in Feynman diagrams, or something else?
But it is both things you describe, because it depends on which point of view you take. Like if you are doing just the Lagrangian formulation, I'm really integrating in and out fields as like carrying out the carrying with the integral over alpha and beta and getting the result. But those steps that you do at the level of the Lagrangian, they also have a graphical representation, and the graphical representation is just what I'm describing here. So, so it is both the things that you describe.
Yeah, but it's like a computationally demanding task, right? It's not super straightforward. It's something you can basically guess. It's something you really have to do the computation to.
Well, here, because you mentioned loops, right? But here, I don't really have loops because I'm doing computation at Born level.
Okay,
so all of my Feynman diagrams are kind of tree-level like.
I see. I see.
Yeah, I'm doing. Yeah, I'm doing the transformation on those graphs, on the tree-level graphs.
Okay, I see.
Right. And after you do these steps, we get this result, which is like the free theory case I described before with this dressing. And this dressing gives you all the supersymmetry, carries with all the supersymmetry. Again, we can notice that the determinant can be expanded into a sum over vertices. And we can, again, absorb the 2-valent vertex into the kinetic term. And this, again, serves to modify the 4D propagator into a 10D propagator that has a pole at x plus y. So this is our final formulation that gives an explicit 10D structure and gives you a way to compute this correlator of determinants by using these vertices that are dual to faces on the original formulation. Well, here in this graph, I'm just representing, let's say, twistor space computation versus the graph. This is more like graph-like or fat line notation. So here you have these CP1 lines where the determinants live, and you send these CP3/4 propagators between them. within the line between these points, you have this CP1-2 propagator. And as I said, you collapse this, and then you get, you will see that what you obtain are now vertices where these propagators enter as weights. So here on the right-hand side is more like the graph formulation, where this square is the original part of the graph on the original matrix model, and then the dual corresponds to collapsing this face into a vertex. But now the vertex knows about all these 4 operators at once. So these are the features of what we call the raw model. Well, using this more manifest ND structure formulation, we have done computations, and in general, what we obtain is some results for the correlators of these determinants, which take this form where you have the superconformal invariance. So these SUSY operators should be written in a basis of superconformal invariance, and the coefficients of the superconformal invariance are polynomials on this 10D propagator. So this is how we make more manifest that that this correlator have a 10D structure. And now this is something that we are currently working on. Now that we have this shape, this is more amenable to attending a limit that we claim gives massive amplitudes in the Coulomb branch. So basically, our map is that when you have this variable going to 0 in the dual where we have the massive amplitudes, this will correspond to the on-shell mass condition, where now this P maps to X, and the mass of the particles in the amplitude, they come from the R-charged part of our determinant operators. So we are still currently exploring this tending a limit, but we already achieved part of our goal, which was making a formulation with this 10D structure manifest. Well, here I just present some result. It turns out that up to 4 points, there is no really supersymmetry. I mean, there is all the higher super part just vanishes, and you obtain a purely boson answer. Here, everything expressed in terms of this Dij. Starting at 5 points and higher, then we start getting these superconformal invariants that have Grassmann variables. At 5 points, we only have 1. And then at 6 points, we already have 8. And so it starts becoming more complicated. But as I said, all the answers have this shape with coefficients within the structure. Okay, so this is my final slide.
Just one question. I guess it was Haslop that had some conjecture about the extension of your result for 10D symmetry for 5 points. Did you check his conjecture, or
yeah, so this is currently what we are studying. Right, because previously with Simon, we had this conjecture which was based on data computed by you and different people. And it was everything about the 4-point correlator of, in this case, let's say 4 determinants. But now, as you can notice in our formulation, there is nothing special about the number of determinants. We have access to any number of determinants by using this matrix model. So yes, we are ready to ask the question of how does this conjecture look like for higher points. And yeah, I think what we have done up to now is one step towards that, and we still need to study more the tendinal limit, but we haven't really performed this limit yet. But yeah, I can update you soon. Right. Okay, so just let me give you some outlook. So it's exactly what Vasco was asking about, is really exploring more the tendinal limit and the connection to massive amplitude. It will be actually interesting to see if what I describe as matrix duality or just graph duality, it would be nice to see what's the string theory perspective of this matrix duality, whether where we are doing very easily with some graphs, maybe has a deeper meaning in string theory, some nice duality in string theory. And there is another question that, well, the main object of my talk has been this giant graviton, which are determinant operators, or they are also D3 branes in the bulk dual. However, this conjecture I've been talking about, the relationship with massive amplitudes, there is already a version of it by Maldacena and Aldai, where the main object is actually a D-1, it's a D-1 brane in the bulk dual. So of course, there is the obvious question of how this D-1 brane of Maldacena and Aldai, how does it, how is it related to our giant graviton, our D3 brane? So this is also something we would like to know the answer to. And of course, well, the whole talk has been about loop integrands, which is basically weak coupling exploration, but it still allows you to give all loop conjectures. But of course, it would be nice if we address this problem at finite coupling, and for that, it would be nice to develop the integrability of these correlators of determinants. Okay, so this is the end of this is what I wanted to present to you today. Thank you.
Okay, thank you very much. Let's thank guys. And now we have time for questions.
What is known about the massive amplitudes?
I think very little. I think there are some papers that have computed some 5-point function, even 6-point function. So taking the tendinal limit of our determinant correlators, we are going to be able to match with these few computations of 5-point and 6-point. But there is no more than that on the literature. It is harder, I think, to do these computations, so that's why. If our conjecture works, I think maybe we have now a way to get access to these massive amplitudes, a more systematic way to compute them.
Do you think you can say something about strong coupling?
Well, no. Well, like what? I don't have a comment about strong coupling. Just the. I mean, it's true. The full talk has been about weak coupling or loop, but of course, this argument by Aldai and Maldacena is something that it's really finite coupling or maybe more strong coupling friendly. And as I said, there is this bit of a mystery for me that in their case, they have D-1 branes, but in our case, we have D3 branes. So yeah, I need to understand more about this string theory side or the strong coupling side to relate the D3 with this D-1 instantons. But yeah, I don't have any checks or anything about the strong coupling regime.
It was more on for 4 points that there was this this 10D symmetry strong coupling, right? That was discovered by Simon, and then you found out that there was also a 10D symmetry weak coupling.
Right.
For 4 points. So do you think you will be able to say something about that for higher points?
Yeah, but this because first of all, we don't understand. I mean, what you just described is that in two different regimes, my case, which is more weak coupling, and Simon and Ankoy, who did the strong coupling, or supergravity, right? The strong coupling that is dual to supergravity. We don't really understand the relationship between these two 10D symmetries. I mean, is the same observable, both manifesting some 10D structure or 10D symmetry, but I cannot say that it's the same 10D symmetry that is just that we are observing like a weak and then a strong coupling. I mean, the reasons behind why we have this 10D structure could be completely different on these two different regimes. So having a statement about 10D structure, a weak coupling from my formulation about 5-point or 6-point does not allow me to jump and say that you will observe it as well for the strong coupling supergravity regime. So there is some missing link there. Yeah, what I do cannot be carried over for the supergravity side.
Yeah, right. Yeah. But for 4 points, I guess it was essential to know what was the superconformal invariant, right?
Right. Yeah, for the 4-point integrands. Yes.
Yeah.
Right. Then for higher points, there are more superconformal invariants. Some of them we have already worked out in terms of the CP1/2 on-shell propagator. We don't yet have a systematic way to get them all. And as you know, they grow with the number of operators.
Yeah.
So we are still at the stage of doing kind of brute force computations where we get, we've done already 6-point and we've done also 7-point. At 7-point, I believe there are already 20 superconformal invariants or something of that order. And yeah, so this is the generic form, but then it's really a sum and a sum over all the invariants. And this is something we don't control yet very well. Something we are trying to do is to get a different matrix model formulation. So yeah, maybe I should say that something I emphasized a lot in this talk was that I get this 10D structure, which would be in this coefficient.
Yeah.
But the way you get this superconformal invariant from our formulation, it's not straightforward. First of all, because as I explained, there was a gauge choice that I needed to make the action Gaussian, and that requires including a reference twistor. So everything is polluted by this reference twistor. We have lots of spurious poles that depends on this reference twistor, and we know that at the end they all should cancel once you add up all the terms. So that's still the way we are getting this superconformal invariant. We still need to add many terms coming from all these vertices to get this superconformal invariant. But we are currently thinking whether there is a reformulation of the matrix model where we not only make this structure manifest, but instead of having this delta propagator that carries the Grassmann part, we maybe have a basis of superconformal invariance. So the dream would be to have some here exponential of SUSY invariance times the trace of rho, like some vertices on rho, such that now everything is manifest, the cancellation of the spurious poles of the reference twistor and also the 10D structure. So this is something we are aiming at currently, but yeah, we have some progress, but it's not clear we are going to succeed. Yeah, so this would be a better matrix model that makes everything more manifest.
These superconformal invariants, are they also new results or?
Yes. I think there is a paper by Heslop and Sokachev and Chicherin and collaborators where they work out the 6-point NMHB. So that invariant they work out should match with this one here. But then for 7 points, the ones we have are novel. So yeah, we are also kind of going beyond the state of art on that side, on getting the superconformal invariance.
Any other questions here or at home? No? Do you have one?
No.
Okay. Okay, if not, let's thank Frank once again.
Thank you. Thanks for the invitation.
No, thank you for accepting.
Yeah.
Very